In this video, I'm going to talk about a nonlinear application of the operation amplifier, which is the multivibrator. I will introduce this application and then I will focus on the explanation of the circuit itself of the multivibrator. To implement a linear application of the operation amplifier, we can settle different implementations, but in this video I'm going to focus on the implementation which uses the operation amplifier with positive feedback, which is the multivibrator. The multivibrator, this would be the block diagram of the multivibrator in which we have no input at all, so the input voltage is zero, we don't have any input voltage, we just have the supply of the operation amplifier. And with this zero input, we obtain at the output a square waveform with a fixed oscillation frequency. And how can be this done? Well, this would be the circuit implementing the function of multivibrator. And we're going to analyze the circuit. As you see, we don't have any input at all in the circuit. We just have the supply voltage for the operation amplifier. And here at the output, we obtain the square waveform. Let's demonstrate this analyzing the circuit. So, to analyze the circuit, because we have negative and positive feedback, we have to know previously that the net feedback of the circuit would be the positive feedback. That's why we can use the methodology of analysis of a positive feedback or no feedback at all operation amplifier. So, taking this into consideration, I am going to follow several steps to analyze the circuit. The first step would be to calculate V plus and V minus of the multivibrator. So, the positive voltage in the positive terminal, the voltage we have here, would be a portion of the output voltage Vs, because this is a potentiometer in which the low resistor is A times R. So this would be Vs times A times R over the total resistor, which is R. So that makes that the V plus voltage is a portion. Remember that A is going to be lower than 1, so a portion of the output voltage. And for the negative voltage, V minus, if we follow the wire, this is connected to the capacitor. So V minus is going to be equal to the voltage Vc in the capacitor. Once we have calculated V plus and V minus, I'm going to follow the second step in which I'm going to suppose one state of the operation amplifier. And I'm going to suppose, in this case, that V plus is bigger than V minus, so that the output of the operation amplifier is going to be plus saturation voltage. Okay, in this case, what I have is the charge of the capacitor. In the last branch of the circuit, we have the saturation voltage, then resistor R1, and then the capacitor. So, if initially the capacitor is discharged, when we have a saturation voltage in this terminal, this will lead to the charge of the capacitor. So, if I represent here the time evolution of the voltage of the capacitor, I will start from 0 and then I will have a progressive charge of the capacitor, an exponential charge, until the saturation voltage. Okay, so Vc, which is V minus, is increasing until the saturation voltage. But when will this change? When will we have the change of state? If Vc is increasing, which is V minus, there will be a moment in which I will have the change of state. And this will occur when V plus is equal to V minus. So when the charge of the capacitor is equal to V plus, which in this case is going to be A times Vs, which is the saturation voltage. So when Vc reaches a portion of saturation voltage, let's imagine we have here this portion A times Vsat of the saturation voltage here, when the capacitor reaches this value, there will be the change of state, so that the output will switch from the high state Vsat to the low state minus Vsat. Then, let's suppose we are in the second state. We have that V plus now is lower than V minus, and the output of the operation amplifier is minus Vsat. So in this case, we will have that the capacitor is connected to a voltage which is now negative. So this will lead to the discharge of the capacitor. So from the final point, the capacitor will be discharged until minus saturation voltage. However, we will have a change of state when V plus is equal to V minus. That means when the capacitor reaches the value of V plus. How much is V plus now? Is A times Vs, but Vs is minus saturation voltage. So I will have that V plus is minus A times Vsat, which is lower than Vsat, so somewhere here, minus A times Vsat. So when the discharge of the capacitor reaches this value, I will have the change of state and the output will again reach plus saturation voltage. Okay, so the capacitor will start again with the charge until it reaches A Vsat, and so on. We can go on with this evolution. The change of state occurs when the charge and discharge of the capacitor reaches a certain value. So we can conclude that the output of the operation amplifier is a square waveform, and V minus follows the charge and discharge of the capacitor. So from no input we have obtained an oscillation voltage which is a square waveform. This is why this is called an oscillator or a multivibrator. In this other case, we have this other multivibrator in which we have added here two diodes, two Zener diodes, to limit the voltage we have at the output. Instead of having the saturation voltage or minus saturation voltage at the output, we are going to have a voltage given by the diodes we have here. So when the output of the operation amplifier is plus saturation voltage, I will have diode 2 on and diode 1 in the Zener mode. So the output voltage will be the voltage of the diode plus the Zener voltage. So that means that I can limit the voltage at the output. Instead of having plus 15 volts, for example, I could have 5 volts to have an output, a TTL output, for instance. Okay? And when the operation amplifier is minus V saturation, I will have minus the diode voltage minus the Zener voltage. So this would be the same voltage but negative. So this is another case of a multivibrator circuit in which Vs can be regulated by the voltages of diodes. In conclusion, this multivibrator gives a square waveform with a fixed oscillation frequency with no need of an input voltage.